So now we will move on to our afternoon lecture, which will be given by Prof. Ubi. And Prof. Ubi is a professor of mathematics at Koblenz University of Applied Sciences in Germany. And he has a doctorate in astrophysics from University of Bonn. And he has worked as a researcher, and he has been part of the CNC research laboratories, NEC Europe, and currently he serves as a professor at the University of Applied Sciences, and he's also held some mini schools at NITheCS. So if you've attended some of them, I'm sure you will know him. And if you'd like to know more about his research, you can find his personal website online. So today he'll be talking to us about Monte Carlo methods. So Prof. Ubi, over to you.
Yeah, thank you very much, Jaekel. Can you hear me?
Yes, we can hear you.
Because I had some technical problems a few minutes ago. I hope these are overcome. Thank you very much for your confirmation. Okay, so then I hope I can share the screen. Okay, you should now all see my screen. So welcome from Germany. Unfortunately, I'm not able to visit your beautiful country. And though we had some money from the European Commission, where I have a collaboration with UKZN and the Stellenbosch University and with NITheCS, or via Francesco Petroccione, the organizer of this NITheCS part. Yeah, and I'm supposed to talk about Monte Carlo methods today. My program is a little bit too ambitious, maybe, but let's see how far we can get. I'll try to keep the chat in. Okay, there's some. Okay, so I tried to keep an eye on the chat, but it's probably not possible to do this in parallel all the time. So if somebody can interrupt me if there's an important question, so then please feel free to do so.
Yes, I will monitor the chat for you.
Okay, thank you very much. Okay, so yeah, my name is Uwe Jaekel. I'm a former astrophysicist, and now I'm more in mathematics and artificial intelligence. And a useful tool in many fields is Monte Carlo methods. And I want to tell you more about Monte Carlo methods today. So what are Monte Carlo methods? This is a really wide field, and I can only give a short introduction, brief introduction today. And more or less you can think of it as solving stochastic or deterministic problems using pseudo-random numbers. The original Monte Carlo method is basically a method for quadrature. What is quadrature? It is the numerical calculation or the estimation of integrals. You can use it for computing expectation values. Yesterday you had an introduction to probability and statistics, and many statistical questions can be solved using Monte Carlo methods. But you can also solve problems that don't sound that statistic or probabilistic by nature. So you can solve, for instance, for high-dimensional definite integrals. And you can, in particular, compute integrals over very complicated and irregular shapes. But there are also many other applications that can be transformed into Monte Carlo methods, including the solution of partial differential equations. There's a deep connection between Monte Carlo methods and stochastic processes and partial differential equations. There are many, so that's one of the bread and butter methods for computational finance. So in computational finance, I guess something like 60–70% of the methods are Monte Carlo methods. and it has a big impact on computational statistics, in particular on Bayesian approaches. As you have seen, much of statistics today is done on the computer. And in former times, you had to look up tables. Yesterday, you heard about that. And this is no longer necessary. And you can do much more complicated computations. First, as a motivation, what are the advantages of Monte Carlo methods? As you will see, they are comparatively easy to implement. They are well suited for high-dimensional problems, and in some cases, they are actually the only known methods for problems that would be otherwise intractable. So there's no competition for Monte Carlo methods for some, for instance, for high-dimensional integration for a general problem. I hope to be able to give you some insight to that, but let's see how far we can get today. So what methods will we use? Basically, Monte Carlo methods, you can think about Monte Carlo methods as statistics and probability theory, done with not a sample of a certain population, but your population will be generated by the computer. So it's just statistics with your subjects generated by the computer itself. And the population is called pseudo-random numbers. So what are pseudo-random numbers? In fact, it's actually a very difficult problem to produce real random numbers. So the quantum physicists that you have heard today can tell you something about it. So quantum algorithms are actually used for quantum random number generators, but still these are pretty expensive resources. And what we actually are using are deterministic sequences that appear random for all practical purposes. This is a very vague description, and I could go into more detail, but it's getting very complex very fast. So I leave it at that. But they also, these are not real random numbers. It's not really random, but it's a deterministic sequence. If you know the previous, or there is a connection to the previous random number when you generate the next random number, which appears like statistically that they are statistically that they are statistically dependent, but actually they look independent for all practical purposes. Yeah? So I will not go into much detail, but there are statistical tests and some tests how you can check whether your random numbers are random enough. And some of the early popular pseudo-random number generators have actually failed these tests at one point in time. You are probably familiar with the generation of pseudo-random numbers. You might have seen it. So you have produced random numbers with some tool, Excel or Python. And just as for a short demonstration, what we can do. Sorry, I forgot to. This is maybe an important advantage. In Monte Carlo methods, we are generating random numbers, and we these look very random. So the question is, can we reproduce our results, or can we have other researchers reproduce our results? And in order to do that, that's an advantage of these pseudo-random numbers, a distinct advantage, that we can actually produce, create reproducible sequences of really randomly looking random numbers. And this is done with a seed number. You may have seen this. Yeah? So let me give you a few examples. I print here in this piece of code, I print 3 random numbers. The first one is from a is uniform from a uniform distribution between 0 and 1, uniformly distributed. Yeah? So there's not a peak of this distribution, but every number has the same probability to be drawn, the same probability density to be exact. So this is done. I refer here to the methods provided by NumPy. So or NumPy, I don't know how you used to pronounce it. I import NumPy as NP, and NumPy contains a library, a random library, providing us quite a lot of random number generators and functions. And one of the functions is rand, similar to MATLAB. If you produce, if you call NP random rand, then you get this random number here. So the first one will be 0.78 and so on. So this is as we want, as we had planned originally, this will be a number between 0 and 1. Of course, in statistics and probability theory, one of the most popular distributions is this nice bell-shaped distribution, the standard normal distribution. And you can draw from a random number from the standard normal distribution using a very similar looking function called rand_n. So this creates a random number which is between between minus infinity and plus infinity, but it has a peak at 0, so the maximum is 0 and the standard deviation is 1, or the variance is 1. And you see here actually we have a negative number. And the third number, we will use this later in my presentation or my lecture. You can actually also draw from exponential distributions. So the probability density is actually exponentially decaying. And you can do this using the uniform distribution and then taking the logarithm of this uniformly distributed random number and multiply it with -1. So this will be an exponentially distributed. So it's also peaked at 0. It will yield a random number between 0 and infinity, 0 and plus infinity. So this can never give a negative result. And then this peaks at 1. Yes. Sorry, it peaks at 0. If I so this is one run of this code block. If I run this code block again, I get different values. Yeah, and you see this still is between 0 and 1. This is randomly. This actually is between 0 and 1, but could be negative, could be larger than 1. And this is must be a number between 0 and infinity, with most likely, no? So here I do a couple of runs. And to show you the seed, if I take a random seed, initialize it, for instance, with the famous number 42, then with every run, here you see that this is actually run again and again. If you look at this number here, at input, you see this is always the same sequence that I get. So that's the purpose of the seed numbers. You get reproducible sequences. And if I comment it out again, then it's getting random again. So we need some facts from probability and statistics. And I want to give you a brief reminder on probability and statistics. So first, we need to know what is an expectation value of a random variable. Let's start with a discrete case. So let's say x is a random variable, and this random variable can, there are n possible events. And so these are fixed real numbers. And these are discrete distinct real numbers, and each of them comes with a probability P of k. What is the expectation of this random variable? This is just the outcome, the result of the draw, multiplied with the probability that the probability of the event, that x is actually equal to xk. So every outcome is weighted with its probability. This is the so-called expectation value. And P is a probability. In the continuous case, and today we will talk more about the continuous case. In the continuous case, we don't have discrete probabilities, but we have probabilities not for 1 to n, but for every possible outcome. So every possible outcome has a probability density P of x, and the expectation value that will then be the integral over P of x times x dx. So again, this means that the outcome is weighted by its probability, and you integrate it over this. Yes? So you can regard the integral as a continuum limit of this sum. So this is fact 1. The next thing that you have to know is the variance. So what is the variance? You can express the variance also in terms of expectation values, and the variance is the expectation of the mean of the square of the deviation from the expectation value of the random variable. So the expectation of the squared deviation from the random variable. And using the facts that we or using the definition here, you can show that this actually is exactly the same as taking the square of the expectation value of the square of the random variable minus the expectation value squared. So usually this is not 0. Yeah, so don't make this classical mistake. You cannot draw this 2 outside of these brackets. Yeah, so E of x squared is usually larger than E of x squared. And the standard variation, this is just the standard deviation. This is the square root of the variance. And think of the standard deviation as a typical deviation from the expectation value. So if the standard variation is, the standard deviation is 1, so then the expectation, the typical value will be more or less something like 1, maybe 2, maybe it's 1/2, but it will probably not be 1,000. So what else do we need to know? We have to know that expectations are linear. If you have 2 random variables, x and y, and alpha and beta are some constants, let's say alpha equals 2 and beta equals 4, then you can take the expectation of these, of the weighted sum of these variables. And the nice thing is that unlike the exponent 2 that we had before, constants, you can draw multiplicative constants in front of the expectation value. And also the expectation of the sum is the sum of the expectations. So we have a very nice relationship here. And on the next very important fact is that the variances of independent variables are additive. Yeah, and just a reminder, what does independent mean? That the probability that you will observe the value of x, the probability of event x and event y The probability that these occur at the same time is the product of the probabilities that X will occur times times the probability that Y will happen. So this is equivalent to you get if you have information about Y, you don't have any information about X. If you have information about X, you don't have any information about Y. Oops. So I have to get rid of this again. So if we have the independent random variables, and we add these variables up, then the variances add up. So the variance, though in the definition of the variance there is a square, but they have these nice additive this nice additivity property. So the variance of X plus Y is the variance of X plus the variance of Y. And this is an important consequence that you will probably be aware of, or most of you have seen. And this is, together with the linearity of the expectation value, is that the error of averages, so the error of the sample mean of independent and identically distributed variables is proportional to 1 over the square root of the sample sizes. I'm sure, so you have a very diverse background, but I'm sure that at one point in your career you have seen this result, this famous 1 over square root of n. So this is a consequence of the linearity of the expectations. In the variance, we square all these expressions, so this 1 over n can be becomes 1 over n squared, and then you get the sum of the variances due to this nice property that the variance is additive. And now all these variables are independent and identically distributed. So all these variances are the same because all variables are drawn from the same distribution. So this means that let's say that we call one of these variables X, then we have n equal variances, and this factor, this can be factored out and cancels with over one of the n's in the denominator. So we get the variance of this average of these random variables is the variance divided by n. And this leads to this famous law for the, or rule for the standard error. So the error of the sample mean is the standard deviation of the sample standard deviation divided by square root of n. So let's illustrate this with this classical example estimation of pi. Some of you will have heard about Monte Carlo methods, and it's quite likely that they have seen this example. So what is the idea? So we want to compute the the value of pi. So what we do is we take the unit square. So here's 0, here's 1. Sorry about this not great. So and this is should be a circle. So it should close here. So so this is the unit square. And what we do is we will now sample from this unit square, and we know the area of the unit square is, it has length 1, width 1, and height 1. So the area will be 1. Yeah, so this will be 1. This area, let's call it SQ. This is 1. And this area here, this is pi over 4. Yeah, because the area of a circle with radius 1 will be pi, and we have a quarter of a circle here. So the area will be pi over 4. And now what do we do is we draw random points from this unit sphere. Let's say we start, this will be our first point. This will be our second point. This is our third point, and so on. And what we do then, so this is a random sequence of points. So imagine that you are throwing dart arrows to a square, and then you count how many hits do I have. Yeah? So I count the number of hits, and it's quite easy to see that the probability to land a hit, to land inside the circle, this will be the ratio of this area, so pi over 4, divided by a. And this means that, and a is 1. Yeah? So pi over 4, that should be, pi should be 4 times the number of hits, where a hit is means you hit this quarter of the circle, divided by number of trials. This will be our estimator for pi. So throw this into the garbage again. And let's see how this can be implemented. So this is, and just for fun, I'm using not NumPy, but only the random library that comes with Python just to show you another possibility to draw these uniform random numbers. In the random library, it's the function is not called rand, but uniform. So what we do is I define a function, make it a function. And this n will be the number of attempts, the number of trials, the number of points that we draw. So this sum is a counter. We count our hits that are checking whether or not we are inside the unit sphere. So we have to draw the x coordinate of the point, of a random point in the unit sphere, unit square, sorry. And its y coordinate, that will be another uniformly distant. Then all we have to do is to check if the sum is of the squares. So again, so all these points here on this circle fulfill x squared plus y squared is equal to 1 squared. Yeah? So if the sum is less than 1, they are inside the circle. If the sum is greater than 1, then they are outside the circle. So, and if they are inside the circle, so if we landed a hit, we drew a point inside the circle, then we increase the sum of hits. Yeah? So after that we have done our n iterations, then we return the sum divided by n multiplied with 4. And this should be an estimate of pi. Let's do it 100 times. Yeah? So this draws 100 points, and you see, let's do it a couple of times. You see we get results that are around 3. Now, we want to get, so the first digit seems to be more or less okay. Yeah, so it's more or less 3. And now, in order to get the second digit as well, maybe I can because I don't, let me see if I can see at the chat. Maybe you can enter in the chat. Just enter some guesses. How many points do we need in order to get this second? Or when can we be sure that we get the second digit right as well? That means we have to decrease the error by a factor of about 10, I'd say. So please write your guess. Somebody write a guess into the chat. No results so far. Okay, so yeah, then I will just provide you the answers. So we have this square root law. Yeah, so in order, here we take an average. Yeah? So this is a kind of average. We divide by n. In order to get it, by a factor of 10 better, because the average decreases like 1 over square root of n. So if we want to improve the accuracy by a factor of 10, we have to do 100 times more samples. So it should be something like 10,000 samples. So that should be give us a better estimate. Yeah, and actually you see it's close to the 3.14 always. Yeah? So actually we're a little bit better than we wanted it. Here I show you another estimation, another implementation of this, which is a little bit more efficient, and where we can get an idea of this of the standard error. So what I do here is I just want to make sure, is it still possible to hear me? Because I had no reactions on the Slack. Could you just give me, because I had some technical problems before. Okay, that's suspicious. Ah, okay, I was looking into the wrong channel. Okay, but this means that I still can be heard. Okay, just. Okay, yeah, there were some good guesses. Yeah, so a factor of, okay, well done. Okay, so thank you very much for correcting me here in the chat. Okay, so you may have heard in the other courses that it's not always a good idea to use for loops. In particular, if you go for performance, it's better to vectorize it. So I show you here another implementation making use of NumPy. So what we can do is we generate all these random numbers in one go Yeah, so and this actually calls C routines. So we generate not only one number, but we generate directly 1,000 random numbers, or maybe more in a moment. So these are the x coordinates. These are the corresponding y coordinates, and then we check with a logic. We do a logical check. So this will be a hit will contain true and false, or zeros and ones, that will be interpreted as zeros and ones. And I make I plot it into a figure. Yeah, so here I have one go, and the nice thing with Monte Carlo methods is that you also get an error estimate. Yeah, so all we have to do to find out what is the error that I make, all we have to do is to take the standard deviation of the hit. So our hit will be 0 or 1. So and our output will be 4 times hit over n. So this will be our average. And the standard deviation of the hits divided by, or 4 times the hits, divided by the standard deviation of n, that will be the error of the estimate. And that's a very nice property of Monte Carlo methods, that you get an error estimate as well. So not only do you get the error, but you also get some estimate how wrong or how correct you are. And this is this is on a 68% confidence level, so 1 standard deviation. If you're more into statistics, you may know that you often prefer a 5% confidence interval, and this should be 1.96 sigma, as you know. Yeah, so this will be the 95% confidence interval. Sorry, I should have put it here. So this will be a 95% confidence interval. So in 95% of the cases of your simulations, your error will be not be larger than 0.1. And you see this is correct. Yeah. So and if I increase it to 10,000 as we did before, my estimate of the standard deviation shows me that these you see the points are denser now, and the approximation has gotten better. So, summary so far. Monte Carlo methods are often easy to implement. What we are doing is estimating expectation values from sample means, and the sample standard deviation of these random variables that we are drawing. These divided by square root of n provide us with an error estimate, which is incredibly useful. Yeah, so let me look at the chat, whether there are some questions at the moment.
Yes, there was one up, Prof, about the applications in astrophysics. In the general, so in the chat, so there was a question about applications of Monte Carlo in astrophysics.
Yeah, so they have many applications in astrophysics, in modeling, for instance. I myself used it for to discuss cosmic ray transport. There are Monte Carlo methods where you want to find out for how the acceleration of cosmic ray works, for instance. So that's one application that I have in mind. The Monte Carlo method actually goes back to the Los Alamos project. So it was used to stimulate or solve problems with in the development of the nuclear bomb. Not a nice application, but actually, you know that in the sun, there are nuclear reactions, and so you can apply these methods as well for radiation transport and many other things. So there's really a huge number of applications, and I cannot give a complete answer today. Yeah, and any further questions you are aware of?
No, I think you have answered all of them.
Okay, thank you. Yeah, so let's proceed. Just for completeness, and in order to emphasize this point with the variance, you can also come up with another Monte Carlo methods for the computation of pi. And this, you can also regard this as the area under the circle. Yeah, so why is this the area under the circle? Let me get back to this famous drawing. Yeah, so here we have this relation, x squared plus y equals to 1, and you can, so this is equivalent to y is equal to 1 over 1 minus square root of 1 minus x squared. That means the area of under this curve here, this will be this estimate of pi. So that's an equivalent, but one-dimensional. In this case, we have only one variable, a one-dimensional representation of the same problem. We made it look indeterministic in our previous example, yeah, by drawing random numbers. But this does not look random at all, right? So how can we make it random? So our integrals of this form here. Sorry, this is that was a bug in my slides. So the area is of this form. We have an integral of a function, and the function in this case is square root of 1 minus x squared. This doesn't look like an expectation value. There's no probability inside, but actually you can rewrite it as an expectation. Because imagine here's a 1, so we just add a 1 or multiply this function with a 1. And the 1 happens to be the probability density of a uniformly distributed random variable. So what we do is we take we draw a random variable between 0 and 1, and then take f of x, so the square root of 1 minus x, and average it. Take the average about it. Yeah? And this will be our Monte Carlo estimate. So our Monte Carlo estimate is just draw random samples from between 0 and 1, just a call to rand, and then take the average of square root of 1 minus xk squared. So let's implement this to compute pi. Yeah? And you see, this is really easy, really simple. Try to write an integration routine with another method that is shorter than this one. Maybe this is not the best method, but it's a method, and you can implement it easily. Yeah, so let's start with 100 points again. And so what we have to do is we sample 100 points uniformly between 0 and 1. Then we take apply this function. So take the square root of 1 minus x times x. Take the mean of these functions as the estimator. and divide the standard deviation of this function divided by square root of n. And then we get our error estimator. And if I want to have a 95% confidence interval, so I want to be 95% right about my assumption on the error, I multiply it with 1.96. And then we get this estimator. And we also get an error estimate. So we know this is 0.17. Let's which means with if we increase this by a factor of 10, then we should get our first digit right again. So what did I want to tell you by this? Even it does not look like a probabilistic problem. You can make it probabilistic in many cases. Then you can look. Can you ask yourself the question, which estimator is better, this 1D estimator or the 2D estimator? And oh, sorry, is the next bug. Okay. I won't go into details. You can look it up. It turns out that the estimator is actually that the 1D estimator is actually better than the 2D estimator because it has a smaller variance. And you can find it out by just computing the variance of the distribution of your random variable. So as an exercise, and maybe we don't have time enough for to make it really an exercise, because I think we have a short break at 3, if I'm correct. But let me stop before the break to solve this more complicated looking problem. Yeah. So we want to estimate an integral which looks more complicated. In particular, it's an indefinite integral. So our integration is running from 0 to infinity. And this integral that we have defined here is the so-called gamma function. And gamma function, that's a generalization of the factorial of a number. So gamma of n, if n is a natural number, is the factorial of n minus 1. So n minus 1 times n minus 2 times n minus 3 and so on up to until you reach the 1, and then you stop with taking the product. And this is a generalization, and it happens that gamma of 1/2, that will be square root of pi. That is a point where we will check this result. So again, this does not look like a probabilistic problem, but again, here we can regard the exponential function. This is the density of a distribution, namely the density of an exponential distribution. And what I told you is that if you take a uniform distribution, that was what we did in the beginning. If you take a uniformly distributed random variable, take the logarithm of it and multiply it with -1, then you get a random variable that is exactly distributed with this density. So the density will be just an exponential function. It's not too difficult to prove it, but I have to skip the proof here. So let's implement it, and remember there's a definite integral involved, and this should make it look, this might make it look complicated, but actually the computation is pretty simple again. So we take a number of random points. Let's start with 1000. And here, I want to take the argument of the gamma function, which shall be 0.5, 1/2. And it should turn out that this is the square root of pi. So we can take the NP square root of you see, this seems to give the same result. Yeah, so we draw uniformly distributed random variables. Then we take the logarithm, multiply it with -1. And then we have to evaluate this random variable with the other argument. So with this will be our function of the random variable. So the random variable will be taken to the power of z-1. Yeah. And then the Monte Carlo estimator will be just the mean of this distribution, of this sample. And we can get an error estimate dividing the standard deviation by the square root of n, of the number of attempts that we made. And this will be compared. Here this again is the 95% confidence interval. And we compare it with the gamma function provided by SciPy. So you learned about SciPy in the previous lecture, and it contains also some special functions like the gamma function. And you see, this gives quite nice results, and we can evaluate it with a higher accuracy. And you see, it's quite accurate, and also our error estimate seems to be quite accurate. Okay, so what we've seen is the Monte Carlo error scales like 1 over square root of n, which means that to get one more digit correct in our answer, which means to improve the precision by a factor of 10, that's 1 digit. In order to get one more digit correct, you need 100 times more simulations. You have to increase the sample size by a factor of 100. This sounds terrible, but we will see it's actually not terrible if you go into higher dimensions. You cannot get much better than that. So if I'm correct, we have a short break now.
Yes, that's correct.
Yeah, and maybe before we go into the break, let me just briefly check whether there's something in whether there are questions. This question here, what is MC pi 1? That was the name of the function I gave to compute the, I called the function MC pi 1. So I had defined the function in the manuscript. By the way, I will also make the manuscript or the notebook available via GitHub. So we'll be able to find it via GitHub, and maybe I can send, or I will provide the link in the GitHub link in the Slack chat. So any questions? So any further questions? Okay, so then we have a break now for.
Yes, we resume in 15 minutes.